Okay, we didn't finish this in class, so let me go through it right from the start. Um, so this is problem 2. This is the safety test lab. We've got a crash test for the smart car. So to maybe sort of make it clarify that 0.78 meter delta D. And so here I've got a before and after picture of a smart car in a crash test. And oddly enough, the car changed colors during the crash. I didn't expect that, but that was the reality. Um, but the key to note for this 0.78 meters is I've got this car, and these cars are actually done to scale, so they're scaled to the same size. But notice that the car after the crash is noticeably shorter, but the bulk of the car. So here's the car. If we look at that, the bulk of the car being in the center of it, that center now is a little bit closer, and so this distance that car has moved, this is that 0. 0.78 meters. So that's our delta D. So we can sort of say that our delta D, that the displacement of the car, assuming that that the assumption that we make, like I said before, is that we're talking about an object as a point. And so if we consider the point of the car, all of the mass at the center of that car, the center of the car has shifted over, and the center has shifted over by 0.78 meters. And we're going to consider this direction to be our positive direction. Now, when it was originally moving, as it was coming in this way, it also had an initial velocity of 100 kilometers per hour. But as we did our conversion in class, I'm not going to go through that conversion. But if I did the conversion from kilometers per hour to meters per second, this would be 27.77777 meters per second. So that's our initial velocity. Notice that it's also in our positive direction, so this is going to have a positive value. And then, of course, after the collision, my final velocity is equal to 0. And this is the important thing to sort of remember. Like I said, when are we going to start looking? When are we going to stop looking? Well, I don't know what got the car moving. I don't know what it was doing before the collision. All I know is that as it hit the wall, the beginning of me looking is as it's hitting the wall, it's traveling at 100 kilometers per hour. Once it, and that's when I'm going to start looking. That's my initial time. So my initial time equals the first contact with the wall. That's when I'm going to start looking. My final time is going to be when it stops. And that's going to set up, and so my delta t, this how much time does it take, the delta t is the tf minus ti. But I'm not going to worry about, I don't know what time it happened, whether it was 3 o'clock or 2:30 in the afternoon. I don't know, and I don't care. All I know is the delta t is what I'm going to be looking at. So I know that as from a motion diagram, I'm going to have my dots placed farther apart, and they're going to get small rather quickly. We expect this. Again, we talked about our sort of expectations. We'd expect that our delta t should be very small. Less than 1 second is what we sort of talked about. Again, we're using our experiential understanding, things that we've seen. A crash happens in almost an instant, a very short period of time. So we expect this. And then if we're going to go from a high speed of 27.777 meters per second or 100 kilometers per hour down to 0 in a very short time, we're going to expect that our acceleration is going to be very high. And of course, based on our understanding of acceleration, in order for us to slow down with a velocity going in the positive direction, our acceleration would have to be negative with respect to that positive initial velocity. So here's our motion diagram. We've got this period of time. So as we're tracking our position over time, this delta t should be less than 1 second. We expect we know I'm going to have a high velocity, so I'm going to have a steep slope to begin with, and it's going to go up here, and it's going to come to a stop, and this distance is going to be 0.78 meters. This time, which we don't know just yet, is less than 1 second. We expect it to be small. We're going to go from a high velocity down to 0. Whoops. We're going to go from a high velocity of 27.8 meters per second down to 0. And again, over this period of time, should be less than 1 second. And I've got a weird stroke of the pen over here. And then we said we're going to have an acceleration that's negative, and we'll assume that it's uniform acceleration. It actually won't be, but again, I mentioned we're going to be making some assumptions. We just hope that our assumptions aren't so dramatically separated from reality that it's not going to give us any picture of the understanding of what's going on. But we recognize that we're making assumptions, and to keep the math a little bit simpler. So now, all of this setting up is so that when I get to this point where I'm trying to pick my equations to jump in and get the answer, because I know that's what we want to get as the answer. We want to understand the physics at first, and then the answer will take care of itself. So I look at the information that I've got. I've got my delta D, my VI, and my VF. And I want to find the time. That's the first thing that they've asked. So if I look at this one here, and again, this delta X is all delta D. So this one here has my initial velocity, my final velocity. I want to find the time, and I know the displacement. So sorry, this is the one I want to find, and I've got this. So if I rearrange this equation, I'm going to start with my delta D equals VI plus VF. And by the way, multiplying that by a half is the same thing as dividing it by 2. So I'm just going to write it like this. And I've got delta T. And you'll see why I'm doing this in a second. Like before, we've got some nice simplifications. Since my final velocity is 0 in that time that I'm looking at, remember the interval, I'm only concerned from my initial time is when I made contact, and the final time is when I stopped. And that's 0. So this becomes 0. So really, I've just got VI over 2. So what I want to do then is I'm going to multiply by 2 over VI on this side. My 2's will simplify, my VI's will simplify, and then I'm left with delta T. So if I do the same thing to the left side of the equation, I multiply by 2 over VI, I have my delta T. So I'm going to rewrite the equation. I'm going to say that my delta T, I need to scroll down a little bit, is equal to 2 delta D over VI. And now I can plug in my numbers. My 2 is just 2. My delta D is 0.78 meters. And I'm going to divide by 27.77777 meters per second. When I do that, go down a bit further, this will find that the time then was 0.05616 seconds. So kind of meets with our expectation. We have a time that's very, very short, which we kind of expected. So now I've got an interesting situation, because now I've got an additional piece of information, this delta T, that I didn't have before. So if I wanted to find my acceleration now, which the question is asking for us for, I have my final velocity, I have my initial velocity, I have my no, I don't have the acceleration, I have my delta T. I want to know my acceleration. That could work. I've also got this is delta D. I have my final velocity, my initial velocity, I have my delta D, and I don't know my acceleration. I have my delta D, my delta T, my final velocity, I don't know my acceleration, I have my time. Notice I can now actually use all. I could use any one of these remaining equations to get this because I have that fourth piece of information. So why don't I do the simplest one? I'm going to say that VF equals VI plus A delta T. Again, my final velocity is going to be 0. So sorry, this will be 0. And if I subtract my VI from this side, subtract it from the other side, that becomes 0, and that becomes negative VI. Negative VI is equal to A delta T. So negative VI is equal to A delta T. If I divide by delta T on both sides, so delta T simplifies, and then I can state that my acceleration is equal to negative VI over delta T. So that's going to be negative 27.777 meters per second. Divide that by 0.05616 seconds, and I end up with negative 494.6 something meters per second squared. Again, if I compare this, so we've got a delta T that's less than 1 second. We've got an acceleration that's high and negative. This meets with our expectations. And I would challenge you to try the calculations with any other of these equations, rearrange to find the acceleration. You should find exactly the same value. And so that would round out our solution. And of course, we always finish off our problems with a final statement. So our paraphrase for this problem, asking us two things, is that the collision lasts 56 milliseconds and the car slows down at a rate of 495 meters per second squared.